A very brief introduction to factor analysis and including the history or objectives. We also compared the factor analysis with our traditional regression. So all the regression variables are observed, but factor analysis, all of the data, especially, the factors are unobserved. And we also we talked a little bit about the PC, and we did a comparison between PC and factor analysis. Also for PCA, so all the variables are observed, even for the components. Although the components are not directly observed, just like the independent variables in the regression, but components can be obtained by using a linear function to get it. So because components are linear functions of each observed variables. And today we will have example to show how to get the components to see the difference between factor analysis and PCA. So first we're gonna look at the matrix algebra. So in the beginning of SEM1, last semester, we reviewed the matrix algebra. We reviewed the matrix algebra, but we didn't talk about the eigen decomposition, eigenvalues, and the eigenvectors. So we can just look at that part by using an example. And we also have matrix form for factor analysis. We do have example and comparison. So that's today's outline. So first, let's have a review of the matrix algebra. So I have already uploaded a document to ELC. So let's just go through it together. So we have a document called matrix algebra. It's different than the document we used for SEM1, but this document is also very helpful. Also very clear. The logic is clear, and the definition is clear, and also the document is very helpful for it. So for some of you, so if you are very familiar with this part, then you can just figure that. We're gonna talk about the definition. Matrix, it's a bunch of numbers, but if we only have one number, we call it a scalar. In traditional math, we just call it a number. So actually we can also call it a scalar. It's just a number. But suppose we have a lot of numbers, then we can just use some rectangles to put all of these elements inside this table. So it's a rectangular table, and of course it's a quantitative. So all the elements can mean some numbers here. So all of these are called elements. In this case, this is the A matrix. So we have 3 rows, 2 columns, 6 elements. So all of these are elements, and we use Aij to show the position of the elements. So rows I, column is J. So rows I, column J, so Ij. So we have different elements here. And usually we use uppercase, capital letter to show that is a matrix or vector. Vector is also a matrix. Just one row or one column. And we have a lot of matrix application. For example, these. And subject. Suppose we have 100 subjects, then we can have a very long matrix. And the P manifest variable. So that means we can put a lot of independent variables or dependent variables or any variables here. So that's very useful notation. And order. So we have size on matrix. So we have different rows, different numbers. Suppose we have n rows, p columns, that we call the order or size A is n by p. N is the number of rows, p is number of columns, n by p. That is the order or size of the matrix. And if the number of rows and number of columns are the same, n equals p, when n equals p, that becomes a square matrix, okay? Number of rows and number of columns is the same. Vector is a very special vector. One single column, okay, this is one column vector. Or one single row. Okay, if we use a transpose, okay, transpose, then we have a row vector. And the transpose, yeah, transpose is very popular operation. Just change the rows and the columns, okay, change this information. If this is A, then A transpose is here. Okay, so here we have 3 rows, 3 by 2, 2 columns. If we transpose it, we have 2 rows and 3 columns. All the rows are just columns here. Okay, the second row here is just second column here. Okay, this is a transpose. And the order for the size, it's different. Originally P by N. If you transpose it, it's N by P. Okay, of course, you change the rows and the columns. And we use a prime, A prime or AT. Okay, T here means transpose. Okay, usually we use A prime or AT to show that's a transposition. Okay? Transpose. And we have equality of matrix. If these 2 are the same, then each element should be exactly the same. Okay, 1, 1 here, 3, 3 here. So equality. And we have addition, subtraction, multiplication, division. So addition and subtraction is quite easy, just element-wise operation. Okay, so element, do the element-wise calculation, add, okay, and the minus. And we have a lot of laws. Okay, one is called commutative law. Okay, so you can change the order. A plus B is B plus A because it's element-wise operation. Associative law, you can just combine. Okay, so in the beginning, so we combine these 2 together, and actually it's the same. Okay, if you combine the last 2 together. And then add A. Okay, so it's the same. Cancellation law. Okay, if you have same matrix on both sides, you can just cancel that. That's only for addition and subtraction, not good for multiplication. Okay, just only for addition and subtraction. If it's multiplication, you cannot do that. Okay, cancellation law. Transpose or sum. Okay, so we have a sum of these 2 matrices. If we use transpose, it's just the sum of 2 transposed matrices. Okay, quite easy. Then we have something different called multiplication. Okay, it's not so easy as we did in the addition and the subtraction. So we have 2 matrices A and B. If we trying to get the product, of course, we have different types of product. If we use a traditional definition of multiplication, so that's the rule. Okay, so we have a bunch of numbers here, okay, which in A, which are a bunch of numbers here, which in B. If we want to get a product of the A and B, the C matrix, we need to calculate each element inside the C. Each element inside the C is calculated by taking the I. Okay, suppose the position in C is IJ, then IJ. Okay, I means row, J means column. You're gonna take the I's row in the first matrix, the J's column in the second matrix, okay, the B, and then do the vector multiplication. Vector multiplication is this way, okay? It's element-wise multiplication, but you have to follow this way. Okay, the first element here is a multiplication. Second element, and finally you get all the sum of all of these products. Okay, so these one pair, the second pair, third pair, so you got all pairs product, and then get the sum. That is vector multiplication. So each element in C, you have to follow this operation. And this is our example. So we have A here, we have B here. So C, suppose this is the A, okay, this is a C11. C11 means, okay, you have to take the first row in A, first column in B, and do the multiplication. Okay, 2 times 2, 4, and 4 times 1, 4. So 4 plus 4 is 8. Okay, that's how you get the 8. And all the values should be follow this way. Okay, and here, this is 10. Okay, 10, the position of 10 is 1, 2. Okay, the first row, second column, 1, 2. So first row from A to 4. Second column, 3, 1. So do the multiplication. 2 times 3, 6 plus 4 times 1. Okay, this is 6 plus 4, it's 10. And we have a rule called conformable for multiplication. So if you want to do multiplication, you have to make sure these two numbers are exactly the same. So the order for A is N by P. The order for B is B by M. So you have to make sure the PP here, okay, the number of columns of the first matrix is the same as number of rows of the second matrix. Then you can do the multiplication. Otherwise, okay, no way, because you have to make sure the multiplication can be doable. So that's a rule, conformable for multiplication. And what's the order of C? If you cancel these two numbers, PP here, finally you have N and M left. So this is a new order. This is the order of C. Okay? So that's a and also the position is important in multiplication. Okay, so we have left position, right position. Okay, if it's a left, we have pre and post. Okay, so if it's in this case, C equals A times B, then we say that B is pre-multiplied by A. Okay, so because A is in front of B, so B is pre-multiplied by A. A is the left side of B, pre-multiplied. And A is post-multiplied by B. Okay, A here, and B is in the right side of on the right side of A, so it's post multiplied by B, because the position of multiplication is very important. You cannot change the order. Okay, so here A times B does not equal to B times A. So if you change the order of these two matrices, we cannot guarantee that the results are the same. Commutative law does not hold. That's why we have pre-multiplication, multiplication, and post-multiplication. So we have these laws. This law still hold, okay? Associative law still hold, but not for commutative law. Okay, it's not true for multiplication. Also, as I mentioned in addition and subtraction, cancellation law does not hold. If you have this form, you cannot just cancel A and to conclude that B is C. No, you cannot do that. But if the determinant of the A is 0, so that means A is singular, then this one is good. Okay, so it's true only if the determinant, the determinant is not 0. Okay. And we also have distributive law. Okay, so just like a scalar case, we have distributive law. We have transpose of product. Okay, just like the addition, we have transpose of addition, but look at the order is different here. It's a product of A times B, But after you do the transpose, the position of B becomes the first. Okay, so B transpose times A transpose. So if you look at the addition, it keeps the same order. Yeah, of course, the order here doesn't matter. If you change the order, it's still the same. But for the multiplication, you have to change the order. Okay, so if you do the transpose, okay, B transpose times A transpose. And we also have some rules of multiplication of scalar. So that's simple. Okay, so C is scalar A times B. Then each element in B should be multiplied by A. Okay, so here 5 is a scalar, and we have a whole matrix here. So each element is multiplied by 5. And we have different types of matrix. Diagonal, okay, diagonal, that means all the off-diagonal elements here, okay? These are called off-diagonal elements. Off-diagonal elements. These are diagonal elements. Okay, so if all the off-diagonal elements are 0, we just call it diagonal. Diagonal is very useful because it gonna simplify your calculation a lot. Okay, so suppose we have a B matrix here. Okay, so we have 3 by 2 matrix. If you have a diagonal element D, you don't need to just follow that way. Of course, if you use a definition to calculate that the product, it's good. But there's a shortcut. Okay, so if you have A11 element, you can just take the first row here. Okay, take the first row and times the scalar here. And second row times the element here. The third row times the third element here. So it's quite easy for us to get the product. It's very simple. That's for the pre-multiplication. Okay, the diagonal matrix on the left side of the matrix. If it's on the right side, we have a column. Column-wise the calculation. Okay, so here we have diagonal elements here. Then we should follow. Okay, so you should follow this shortcut calculation. Okay, so we have first column here times A11, first element. Second column here times the second element. Third column here times third column. So it's quite easy for us to get the product. So it's trick. It's kind of like a trick. Okay, so but if you just follow the traditional definition, yeah, it's all good. It's all good. And we have identity matrix. If the elements, okay, on the diagonal positions are 1, it's called identity matrix. Identity matrix just like 1. Okay, any matrix times identity matrix is just itself. And symmetric matrix. If you have transpose matrix equals itself, okay, S equals the transpose of S. If you change the rows and the columns, okay, 8 becomes 8 here, 5 becomes 5 here, 4 becomes 4 here. It's exactly the same. So this is called symmetric. Just like covariance matrix, correlation matrix, they are all symmetric. Okay, so you only need to make sure these elements are exactly the same. Correlation matrix, okay? Correlation matrix is one type of symmetric, but you have to make sure not all symmetric matrix are correlation matrix. Okay, we have some characters for correlation matrix. The diagonal elements should be 1, 1, 1, 1, 1, 1, 1, and all the off diagonal elements should be less than 1. Okay, because these are correlations. Correlations we have absolute value should be less than equal to or less than 1. Okay, so this is a range of correlation. So all these numbers should fall into this range. And this is a very special case. Okay, so this one looks like, okay, correlation. Okay, 1, 1, 1, 1, 1 here. And all the elements here are within this range, but still it is another correlation because a correlation matrix should be non-negative definite. So what does that mean? So that means the eigenvalues should be positive, okay, or 0. So it's non-negative. So we're gonna look at eigenvalues very soon, okay? So if it's a correlation matrix, it's non-negative definitely. But if you check this matrix, the eigenvalues, they already calculated these 3 numbers. This one is negative, so it cannot be a correlation matrix. So again, how to get the eigenvalues, I will show you an example later on, okay? And orthogonal matrix. If it's an orthogonal matrix, it has to be a square, okay? It has to be a square matrix. And what does that mean? So the matrix times the transpose of matrix is identity matrix. In other words, okay, so the transpose of the matrix is the inverse of that matrix. So that's a property for, that's a character of the orthogonal matrix, okay? Orthogonal. The transpose and the inverse are exactly the same. Now let's move forward to some functions of matrix. Determinant is a function. I'm sorry, because of the function. Can you still see the screen? Okay. Determinant is a function, okay, a matrix. And the form of the function is not easy, okay? So we can look at some very simple cases. Okay. And of course, the matrix should be square. Okay, should be square. If it's rectangular, then it's definitely 0. Okay. If it's not square, then the determinant is 0. And among square matrix, how are we going to calculate the determinant? Okay, let's look at this case. We have this 3 by 3. As I showed you in the very beginning of last semester, so we should follow this way. We calculate the product of these 3 numbers, calculate the product of these 3 numbers, and then product of these 3 numbers, add them together, and then minus the product of these numbers, minus the product of these numbers, minus the product of these numbers. Okay, so that's matrix A. If we have 2 by 2, then it's much similar. Okay, so you only need to get the product of these 2 numbers, okay, diagonal elements, A11, A22, and then minus this product, okay, the product of these 2 numbers. That's it. It's a simplified version of this 3 by 3. So in this case, it's the product here minus this product. So if we have example 2 by 2, then 2 minus 2 times 5 minus 3 times 4. Okay, 2 by 5, 10, minus 3 by 4 is 12, so it's minus 2. So that's good. So the determinant is not 0. Determinant could be negative, that's totally fine. But if it's 0, we call it a singular. Okay, 0 is not quite good. Okay. If it's 0, then we say that singular. If it's singular, you don't have any inverse. Okay. Now, inverse. Inverse only happens when the determinant of A is not 0. If it's 0, then you cannot get an inverse. So if we have the inverse of matrix, then the product of the raw matrix itself, original matrix, and the inverse is identity matrix. Okay, of course, if you choose the order, it's true. And we have example. So how to get an inverse? Okay, this is a way to calculate 2 by 2. We have to get the determinant of A here. So that's why, okay, so if the determinant is 0, okay, 0 in the denominator part, it's not defined, so you cannot get a solution. You have to make sure the determinant of A is non-zero, and then you can have inverse. And how to get the inverse? We change the position of these 2 elements. Okay, so here, originally you have A11, then becomes A22. Okay? Change the position. And here, originally A22, it becomes A11. Okay, these two positions are changed. And for these off-diagonal elements, just adding a minus. Okay, it originally it's A12, it's minus A12. A21, it becomes minus A21. That's it. Okay, that's it. This is our inverse. Yeah, so only square matrix have inverse. Okay, otherwise it's the determinant is 0. Some square matrices do not have inverse because, okay, if it's singular, if the determinant is 0, if it's singular, then even it is a square matrix, it does not have an inverse. Okay, so inverse of scalar, it just reciprocal. Okay, just 2. If it's 2, then the inverse of 2 is just 1/2. So if this one is 0, then it becomes singular. If it's not 0, we call it non-singular. And we have solution of the equation. Suppose we have this matrix equation. We have A matrix here, A matrix, and we have some unknown parameters or some unknown values here. A and B are known. All of these values are available for me. Then how are you going to get a solution of this equation? So we have this derivation. So first, okay, so we have the inverse of A pre-multiplied, okay, pre-multiplied of this left side part. And the same thing, we have this case. And the A minus A inverse and A canceled because this is just another matrix. So finally, we have the solution of this equation is the inverse of A times B. Of course, you have to make sure, if you want to get the solution, you have to make sure that A is square and non-singular. Otherwise, no inverse, you cannot get the solution. Okay, so you have to make sure this is doable. Okay, now let's look at eigenvalues and eigenvectors. We're gonna use it today. Okay. So, what's the definition of eigenvalue and eigenvectors? So first, you have to have symmetric matrix. Suppose it's called S. S is the symmetric matrix and the order of P. Okay, so that means it's P by P. So, and we have a column. Okay, U here is a column. This column also have P elements. P elements because the order of S is P. Okay, we have the conformable of multiplication to make sure this multiplication is doable. The S P by P times a vector, column vector P by 1. It should be a vector. Okay, it should be a vector. And now let's look at a very good property in this case. So we have P by P matrix here. And here we have P by 1 column here. If you do the multiplication, so finally you have P by 1 vector. This is vector. This vector is just the same U here, the same U here, same vector here, times a scalar. This is just a number. This is a scalar. This is just a scalar, a number. So the U here, for the same U, for the same vector here, the function of a bunch of numbers, the whole matrix is the same as just one number. So that number is kind of like a representative of this whole matrix. Okay, so S is a matrix. We have a lot of numbers here. And then we find a U vector here. It equals the same U here. It is the same U here, same U here. Finally, after we do the multiplication, it becomes a scalar, a number times the same vector, the same vector. Okay, we have the whole bunch of these numbers, but the function, finally, the function just is the same as one number. So this number is very, very important. Very, very important. So we call it eigenvalue, because eigenvalue can just treat it as the whole matrix, but not for all vectors. These vectors are also very special. These vectors are called eigenvector. Okay, so these two components are extremely important for this matrix. We have some vector, okay, with respect to these vectors. The function of this whole matrix is just this number, the eigenvalue. So that's why this is very important. What does that mean? We can just simplify this whole matrix into one number. Okay, of course, we may have several numbers. So we can simplify the whole matrix into several numbers. Those are eigenvalues. Okay, so the L is called eigenvalue, and the U is called the eigenvector. Okay, so we're trying to get these two key components of the matrix. So if we have a symmetric S, okay, so the S matrix, we may have a lot of like eigenvalues. If we have P, because of the dimension of this S, the symmetric matrix is P. So we can have P, these very important numbers. So we can find the P numbers. So the first largest one is called L1, and then we may have a smaller one, we may have a smaller one. Finally, we have the smallest one, LP. But all of these are very important. All of these are called eigenvalues. But for each eigenvalue, we can find a U here. Okay, so if we get, suppose we get the first, the largest eigenvalue here, we can find the eigenvalue to make this equation hold. With not a random vector can make this equation hold. You have to, based on this eigenvalue, and then to got the eigenvector. Okay, so these are associated. Okay, so U1 is for L1, U2 is for L2, UP is for LP. They are associated. And of course, you can standardize these vectors, because vector tell you a direction. Okay, if you think about the math, it's just vector. You can make it longer, you can make it shorter. We can standardize the eigenvector. And if you put all of these P numbers into the matrix in the diagonal entries, you have a diagonal matrix D. Okay, the D is diagonal, just include all of these P elements on the diagonal positions. You can use that, we can call that D. And then we can also put all of these columns. Okay, so use one column, it's called vector. Vector 1, vector 2, vector 3, vector. If you put all of these vectors together, P vector together, it's another matrix. So you can call it a U. Now it's very important conclusions. This U is orthogonal. So we just have a review. We have orthogonal definition. Okay, orthogonal, the transpose of the matrix times original matrix is identity matrix, or the inverse of the orthogonal matrix is the transpose of the matrix. Okay. And we also have these good properties based on the previous derivation. So the S is original symmetric matrix times the U. Okay, U is here. U is a column of all of these eigenvectors. Okay, then what's that? It's just the same U matrix times the diagonal matrix. So D here, including all of these eigenvalues on the diagonal elements. Okay, so this equation is true. Actually, this can be derived from the definition here. This is coming from here. This is for one U. But if you put all of these U's together, okay, here we have one U and put all of these U's together, we just have this matrix form, okay? And then if you do a little bit of trick, okay, the S, you can, because U is orthogonal, the inverse of the U or transpose of U is the same thing. You can times the transpose of U. So transpose U, it becomes identity. But here you have transpose U on the right side. So the S can be decomposed a product of these three components. S is a symmetric. So any symmetric matrix can be decomposed into these three parts. U is the vector containing all of the eigenvectors. D is a matrix containing all these eigenvalues, transpose of this U. So if you got the eigenvectors, eigenvalues, you can use this form to replace the original symmetric matrix. So this is called eigen decomposition. We try to decompose the symmetric matrix by using this simplified matrix. Okay, so here it's very, so this is diagonal and these are the same, okay, and this also consistent with the eigenvalues. So everything become simple, okay. So that's why it's called eigen decomposition. It's very important, extremely important in math and in stats and other engineering areas. Yeah, so this is called eigen equation for S. Okay, it's the same thing here. S times U is U times the dl. It's eigen equation for S. So we have some definitions here. In the previous slides, we called it the non-negative matrix. So what's the definition of non-negative? Definite, okay? So here, if all P values, P eigenvalues, okay, we have L1, L2, L3 to LP. If all of these P eigenvalues are positive, okay, then the whole matrix, the symmetric matrix S is called positive definite. Okay, it's positive definite. Okay. If all P eigenvalues of S are non-negative, so it could be positive, but it could be zero. It's called a non-negative. It's not negative. Okay, then the matrix S is called non-negative definite. Just like a correlation matrix. Correlation matrix should be non-negative definite. That means the eigenvalue of the matrix cannot be negative. If it's negative, then it's definitely not a matrix, a correlation matrix. Okay. And the determinant. Okay, so I show you a simple case to calculate the determinant, but I said, okay, the actual form, the general form is not so easy. But if you have those eigenvalues, the problem becomes much similar, okay? You only needed to get the product of all eigenvalues. Then that is the determinant of that matrix, okay? So it is the product of all eigenvalues. Of course, if one eigenvalue is zero, then the determinant is zero. So if it's, but still it's non-negative. If it's one of the eigenvalue is zero, then still the S matrix is singular because the product is zero. Yeah, it's called a singular, still singular. It's eigenvalue. If one eigenvalue is zero, it's still singular because the determinant is zero. And actually, there's another function called trace. Trace, just like a determinant, but it's the sum of the trace. The definition of trace is sum of diagonal elements. Okay, diagonal elements. For example, in this case, in this case, the trace is just 2 plus 5. Okay, just diagonal elements. It's 7. So the trace of A is 7. So the trace of a symmetric matrix X is equal to the sum of the eigenvalues. So once we have those eigenvalues, trace, okay, determinant and the definition and the singular could be very easy because we can do a lot of calculation. It's a sum of all eigenvalues. It's just a trace. And then we have another function. Okay, we can do a lot of linear combination of random variables. So suppose we have x, okay, we have z. So all of these are random values. We can use a column to show these are random variable. Then we can have this case. Okay, so we can have the x equals a mu plus a times z. So z is a random variable, x is a random variable. Okay, so we have mu is a column vector. It's fixed. This is actually kind of like a fixed part of the linear regression. Okay, so we have the random. This is fixed. This is not random. This is fixed. This is the mean part. And then we have these random, x random. We have a matrix here. All of these numbers here tell us the relationship between the x and z. These are linear relationship, okay, linear combination of random variables. Because by doing the multiplication, okay, we have all of these coefficients times the z, and plus mu1 is just x1. x1 is a linear combination of all of z components. And this is a coefficient. All of these are coefficients, okay? And of course, we have the mean part, mu1. So x2 is also a linear combination of all z components. These are coefficients, okay, coefficients. And then we have the mean part, mu2. So all of these are linear combinations of z. Yeah, so x1 is mu1 plus, this is a multiplication, okay? So a11 times z1, a12 times z2. So it's just a linear combination of these components, okay, these elements. And the xp is this form. Okay, so the matrix or equations of matrix, it just tell us the relationship of all of these numbers. Okay, we use a matrix form to simplify those equations. Otherwise, by using the matrix form here, we may have a lot of equations. Okay, this is just one equation. We have second one. We may have a bunch of equations, but by using the matrix form here, it's very simple. It's very elegant. Okay, it's quite elegant here. So that's for matrix. And the next part is application. So covariance, okay, variance, okay, this is the definition of covariance. Expectation of two products, okay, this is the original row minus the mean of x, okay, original x, original score minus the mean of x, so transpose. Because all of these are vectors, okay, so we have expectation, that is covariance matrix, okay, it's called a covariance matrix of x, capital sigma. Yeah, so this is a detailed calculation. We have all of these vectors. X column here, mu column here, transpose here. And then do the multiplication, we have this part. So this is a covariance matrix. Each element here is a variance or covariance. Okay, so diagonal elements are just variance of that element. Okay, off diagonal elements are covariance, okay, between different variables. So this is an example of application of matrix algebra. Okay, so it's covariance calculation. If it's centralized, then if it's mean 0, we don't need to minus mu. Then it's directly equals to the expectation of x times the transpose of x, okay? Because mean is 0, so we don't need to minus mu 0. Standardized, if you have standardized z, then it's just this one, okay? Because standardized mu is 0, it's already centered. And we have this correlation, this is P is correlation, okay? And this is a covariance if you standardize X, you have the correlation P. That's it. So we also have we also have the further explanation why it's correlation, because the diagonal elements should be 1 because it's standardized, okay? The variance is 1, standardized. And off diagonal elements are just those correlations, okay? These are correlations. Okay, that's it. This is a review for today's class. Now, let's move forward to the factor analysis. As I mentioned, this is the form, mathematical form of our factor model. We can use a matrix form to show all of these equations. Actually, these include a lot of equations, okay? And also, this is a linear combination of a lot of components. By using the previous matrix preparation, we can actually we can actually use the matrix form to show this model. But before that, we can just have a review. Okay, so why here? This is observed. Why? For person I on the J's variable, because we are focused on different variables. We also have a bunch of participants. Lambda is a factor loading. Okay, factor loading to connect Y and F. It's also coefficient. And lambda, there's no I. I don't care about the person's I. Okay, so we have JK here, but we don't have I. The person subscript disappeared. F is for factor scores. Okay, it's unobserved. Factor score is unobserved. And for each individual, we have factor score. For different factor, we have factor score. So we have IK, but we don't have J. Okay, it does not correlate with the J's variable. And actually, this part is called common factors. Okay, this part, common factors. We also have unique factors. We're trying to decompose the factors into 2 types: common part, common for all indicator, all variables; unique part, unique for that variable. Okay, only. So again, this is a typo. I'm sorry. So it should be IA, not BIK. Yeah, this is a review. We have common factors. Yeah, I just got the slides from previous class. Common factors influence more than 1 manifest variables in the set we are observing. Unique factors influence only 1 manifest variables. It's specific for some variable. And the unique factors include the specific factor in the measurement area. So this is the Hash diagram I used in the last week. I also, I trying to have this Hash diagram. So we have some items observed. Okay, those are direct observed items. Those are latent factors. So observed items and latent factors have some connections. So the connections can be described by lambda. It's a lambda. The factor loading tell us if it's strongly connected or not. Sometimes it just close to 0. Okay, some weights could be 0. In that case, we can just remove those connects. And some are really strongly connected. Okay, so by looking at the lambda factor loadings, we can tell the pattern of the factor model. Okay, so now let's apply the matrix form to the factor analysis. Here, I only have this simple form. So what are these? Okay, we have Y is the vector of the previous Y. Okay, so we have a lot of Y here, but actually this is a Y vector. Y vector including P variables. For each manifest variable, I can have 1 element in Y. So the Y here is P by 1, the order. So it include y1, y2, y3, yp. Okay. So suppose this is a math score, this is a math score, this is a verbal score, this is a maybe it's a music score, this is the other test. Okay, so we have so many variables. This is for y. Then let's look at f first. Okay, f is just the summarize the vector of the previous vector. So when we talk about this form, we have a lot of f. Okay, we have f1, f2, f. We have k vectors. We have a lot of f. We combine all of this f, k, f together. We have a vector. Okay, so this is a f is a vector. Have f1, f2 to fk. Capital K. Suppose we have capital K vectors. This is a vector of f. And then we have this lambda. Lambda is just the combination of all of these lambdas. Here we have a bunch of lambdas. Okay, we have a lot of lambdas. We combine all of these lambdas based on this form. Okay, so we have so many lambdas. Then we use a matrix to show lambda. But lambda is really large. Look at the dimension. It's p by k. So what does that mean? Lambda is a huge matrix. It's not vector. Okay, it's not a vector. It's p by k. So we have p rows. First row, second row, p rows, because we assume that there's a p variables. And then how many columns? We have capital K columns. So we have column 1, column 2, capital K columns. Okay. So all of these values are just lambda. Okay. All of these are all lambda values. So the weights or loadings are summarized or are stored in this matrix. Okay, and this is the main part. And of course, we have the residual part. We have the unique factor part. This is the common factor. This is the unique part. It's still p by 1 because the dimension of y is p by 1. P by 1. This is the p by 1. After do the calculation, okay, lambda times f. After do the multiplication, because we have p by k here, capital K by 1 here, we cancel this 2k here. Finally, the product is p by 1. The product is p by 1. So that's a matrix form of factor model. Very simple. That's it. Y equals lambda times f plus u. That's it. So it's much better than the previous case in this slide. Okay. But you have to make sure that the notation in this form. Great. What should we do by using this form? Next, we're gonna do further calculation. Oh, these are assumptions. Okay, yeah. After we put some assumptions, we can do further calculations of the matrix. What should we assume? F and U are independent. F is means for the common factors. Okay, U is unique factors. We assume these two are independent. There's no association among them. U are mutually independent. Okay, these are unique factors. We assume that, okay, U for the variable 1, U for the variable 2, U for the variable 3. These are mutually exclusively independent, okay? And the means of U and F are 0. So we assume they have already been centered, okay? So we have already, that's why there's a no intercept term in the previous form. We assume that, okay, these two are centered. It's a mean of 0. And this is not necessary, but it's useful for our calculation, for identification purpose. Okay, otherwise we may have a lot of solutions. If we try to identify a solution, we assume the variance of the F is 1. Okay, variance, okay, so the F is latent, common factors. We just assume the variance of F is 1 to identify our solution. Otherwise, we may have solution 1, solution 2, solution 3. But if you're trying to get one solution, you have to put some anchor information there. So if we assume the variance of f is 1, then we can have a solution, okay? And let's look at some notations. This is a very common notation. Capital sigma, covariance matrix. Covariance matrix of the original raw scores, okay, 1. So usually we use a capital sigma to show the covariance matrix of 1, okay? We did a lot of calculation last semester. We also have this notation. Phi, what is that? This is a covariance matrix. Covariance matrix, but not for Y. This is for common factors. Y can be composed into 2 parts, F part and U part. So in together, we have the covariance matrix of Y. We use capital sigma. But for F, we also assume the covariance matrix is another matrix. Okay, we use phi to show that is a covariance matrix of the common factors. But we do have the U part, okay? The U part, the residual part. We use either psi or D. In most cases, people use psi. Okay, all of these are very, very traditional notations. If you read SEM journal articles or textbooks, people just follow this way, okay? So if you think about psi, if you look at a psi, usually it is a covariance matrix of the unique factors or the residual part. If you have phi, okay, usually it just means the covariance matrix of the common factors. Capital sigma is for Y, okay? Those are very, very traditional notations. Now, okay, now we have those assumptions, we have those notations. Let's try to do some calculation. The mean and the covariance of the factor model. So factor model is our focus, right? So let's try to use a matrix form to do this calculation. It's really easy, actually, because we have already reviewed the matrix part, and we have a lot of assumptions. Okay, so what is the form of the factor model? That's it. That's it. Okay, and then we try to calculate the expectation. Expectation of Y is just expectation of Y can be replaced by this part, okay? And then expectation follows the expectation rules. It's just the expectation of the lambda and expectation of U, okay? This one is 0, okay? We assume that the U descended as 0. And actually, we can have this form, okay? Lambda times the expectation of F. If you assume the F is centered at 0, then it's just 0. If you do not have that assumption, then it's just F times the expectation of F, okay? That's for the first moment, the mean. Variance, the same thing. Y equals lambda F plus U, okay? Variance, think about the rule of variance. Rule of variance. What is that? Because of the assumption, okay, F and U are independent. We don't need to look at the covariance of these two. We can decompose it into 2 parts, okay? Variance of lambda F plus the variance of U, because they are independent. F and U are independent, no covariance term, okay? Variance of lambda times F follows the covariance, follows the variance rules. What is that? What is that? Equals lambda times the variance of F times the transpose lambda, okay? And then variance of U, think about our assumption. We assume that this term is psi. Okay. We assume the covariance matrix, which is a variance matrix of U, the unique part is psi. Now, what is this? This is the variance of the variance of the common factors. We have assumption, we assume is phi, okay? So finally, we have lambda times phi transpose lambda plus psi, okay? That's a covariance matrix of Y. We decompose and we use capital sigma, okay, capital sigma to show it. So this is the equation for factor model. The covariance matrix of Y is lambda times the covariance matrix of the common factors times the transpose of the common factor loadings plus the common factor, the covariance matrix of the unique factors. That's it. Okay. This is our focus. Yeah, finally, that's it. That's it. Sigma, lambda times P, transpose of the lambda times plus psi. Finally, for that specific factor model, we derive the covariance matrix. Yeah, in the first semester, we use so many methods to derive the covariance matrix of a specific model, okay? Mediation model or regression model. For factor model, that's it. This is the matrix. That's it. So phi is a P by P matrix, the covariance matrix of the common factors. Psi is a P by P diagonal matrix because we assume all the U are mutually independent. So it's diagonal elements. All the correlations among them 0. So that's why it's diagonal. Off diagonal elements are 0, 0, 0, 0. It is a covariance matrix of the unique factors. Okay. Yeah. So this is especially important to note that the covariance structure does not contain any factor scores at all. If you look at this equation, there's no F, no factor scores. In the very beginning, in this equation, we have factor scores, okay? And even in the factor form, in the matrix form, we have factors. But if you look at the covariance matrix, no factor score involved, no F, no F, no F. I don't care about the F's, okay? Does not contain any factor scores at all, okay? Neither common factors or unique scores, no, okay? In this case, the parameters are lambda, okay? All the factor loadings, we should get obtain those factor loadings, lambda here. Phi, the elements of the covariance matrix of the common factors, the covariance matrix of the unique factors. All of these are unknown parameters, okay? And then having this capital sigma, we have the sample-based covariance matrix S. We're trying to make these two matrices as small as possible, just as we derived in the previous SEM1. We have capital sigma, we have S. We're trying to make the capital sigma and S as small as possible. We have different ways. We can use maximum likelihood estimation method. We can least square estimation method. Okay, so those are methods. Okay, then that's a general form. Usually, we put some assumptions on phi to simplify that form. Okay, so what's the assumptions? So suppose that factors are uncorrelated. Think about the phi. Okay, what is the phi? Phi is covariance matrix of F. Okay, this is a capital F. Okay, so we have, suppose we have F1, F2, F3. We also have F1, F2, F3. So all the elements here are variance or either variance or covariances. So this part is variance of F1. This part is variance of F2. This is the variance of F3. And this is the covariance between F1 and F2. This is the covariance between 1 and 3. This is 1, 2. This is 1, 3. This is 2, 3. So all of these are, this is phi, inside of the phi, all of these are variance or covariance among those factors. If we assume factors are uncorrelated, if the covariance, these parts are uncorrelated, 0, 0, 0, 0, 0. Okay, all of these are 0. We have the diagonal element. We also assume the variance of the factors is 1. In the very beginning, we assume the variance of factors are 1. So it becomes 1, 1, 1. So the phi, we have these assumptions. The phi is just identity matrix. Okay, all of these off-diagonal elements are 0, 0, and the diagonal elements are 1, 1, 1, 1. So it's just identity matrix. Okay, if we have that form, then the capital sigma equals a lambda times the transpose of lambda plus psi. That's it. We don't have phi because we assume that the phi is identity matrix. We assume the factors are uncorrelated and the variance of F is 1. Yeah. So we have this simplified form. And by using that form, we can do a lot of work. Okay. It's called uncorrelated factor analysis. Okay, for example, this is one case. Now, we assume these are independent and we have a lot of observed variables. We also have the residuals. So we have different lambda values here. Okay. Now, let me talk about the communality again. When we have so last week, when we talk about the decomposition of the variance, so I show you a really large bar. Okay, we have a total variance. We have the common variance due to common factors. We have the unique variance. Okay, so we give a definition of communality. The communality is a proportion of the observed variance due to common factors. That's why it's called communality, common factors. So the form is common variance divided by the total variance or the observed variance. Or you can use 1 minus the unique variance over the total variance or the observed variance. Either formula, okay, that is called the communality. At that time, I said, okay, very soon, we're gonna have example to calculate that value, communality. So today we're gonna calculate this value. And we also did a comparison between communality and the reliability. Okay, reliability is for the true variance. So true variance includes the common variance and the specific variance. That is reliability. It's different as a communality. Communality, we just care about the common factors only. I don't care about the unique factors. Okay. Now, let's look at the formula, how to calculate the communality. Okay, for each variable, suppose it's for J's variable, we can calculate its communality. We usually use H to show, okay, H for J. So that's J's variable's communality. Okay. It is a variance of all the J's variable accounted for by all the factors, common factors, by all common factors. Okay. How to do that? Okay. Actually, this is a calculation for each H here. It's the sum of the squared factor loading for all factors for the J's variable. This is for each H. After we get each H, the total variance in the observed variables are explained by the common factors, the sum. Okay, so we have P variables. For each variable, we have communality Hj. So get the sum is the total communality. But for each variable, Hj is calculated as a sum of the squared factor loading For all factors for the J's variable. That's for H part, okay? And then the remaining part, the variance for the unique factors is just 1 minus the commonality, okay? This is due to the common factors. 1, we assume the total variance of factor is 1, okay? 1 minus the commonality part. This is due to unique factors. This is a side. This is just a side part, okay? Unique factors. So we have ways to calculate the H, we have ways to calculate the psi. We got the sum of H. Okay, so how to apply this form? Just look at this case. We have the lambda matrix. Okay, so this is matrix. Okay, so you should have some parentheses here. This is matrix. 4 rows, 2 columns. This is a lambda matrix, factor loadings. The question is, okay, what are communalities? What are sign matrix? What? Before we answer these questions, let me ask you, based on this lambda matrix, how many variables in this case? If I just give you this lambda, do you know how many variables in this model? How many variables in this model? This is a factor model. Suppose this is a factor model. Or let me ask you, how many factors in this case? 2. Good. Then how many variables? Exactly. P is 4. In this case, if I give you this lambda matrix, P is 4, K is 2. Number of factors, 2. Number of variables, 4. So what does that mean? You need to calculate 4 communalities. There are 4 communalities because you have 4 variables. For each variable, you have 1 communality. Okay. So so the question is, what are communalities? What is the first communality? Okay, what is H1? What is H1? Yeah, think about that. What is H1? Think about the definition in the previous slides, okay? It's squared. It's the sum of the squared of all elements, all factors, okay? Loadings, I'm sorry, the sum of the squared of loadings for all factors, common factors. That is called the commonality for the J. J is variable. Okay. Now look at the first variable. First variable. What is the commonality? How do you calculate that? H1. What is H1? It's sum. We have 2 factors, okay? We have 2 factors. You only need to figure out the 2 parts. 2 factors. The sum of squared factor loadings for each factor. What is the factor loading for the first factor? What is the factor loading for the first factor? 0.7. Squared, okay? Squared. What is the factor loading for the second factor? 0.1 squared. That's it. The first commonality is 0.5. Okay, the squared factor loading for all factors, we have 2 factors. Now, what is H2? What is H2? Yes. Yes, that's it. That's it. What is H3? What is H3? Exactly, 0.5. What is H4? Yes, yes. Yeah, 0.72 is and then we can get all the communality. Okay, we can add all these together. We add all of these. we get the sum of the edge I. Okay, I from 1 to 4. We have 4 variables. We have 4 variables here. Sum of these two. That is the first question. Okay, what are communalities? Good. What is a sign matrix? What is a sign matrix? Sign matrix. First, let's make sure. What's the order of this sign matrix? What's the order? What's the dimension? What's the size of the sign matrix? P by P. Specifically, 4 by 4. Exactly. Psi is 4 by 4. Okay, we have some, 4 by 4. And what is this form? Psi is diagonal. We assume that off diagonal elements are 0 because we assume that you are independent. So we have, okay, all of these are 0, 0, 0. But we do have some 4 spots left. So what is psi 1, 1? What is this psi 1, 1? Psi 1, 1. We have H1 here. Remember that psi is 1 minus the H. Okay. So psi is 1. If it's 1, 1, it's psi 1, 1. It's 1 minus H1. Then what is psi 1, 1 here? What is psi 1, 1 here? Exactly. So 1 minus 0.5. It's 0.5. What is psi 2, 2? What is psi 2, 2 here? Yes. This is psi 2, 2. What is psi 3, 3? Yes. Yes. What is psi 4, 4? 0.28. Okay, those are diagonal elements. So this is our sign matrix. Okay, those are our H matrix. So why? Because we just calculated it before. Okay, so that's a communality. Our vector model. Yes, our vector model. Okay. Just an exercise. Okay. Any question? Actually, we have already finished the session 1. We just reviewed vector matrix. Matrix algebra, and then we applied the matrix to the general form here. The general form here. We have the matrix form for vector model, and we did the calculation of expectation and the variance. And finally, we have this form. This is our key equation. Okay, this is our key equation. And by assuming that the phi is a dynamic matrix, then we have simplified the form of the base. Okay. So, any question? Okay, then we can have a 15 minutes break, and the next session, we're gonna look at the principal component analysis. We're gonna apply the eigen decomposition. Okay, eigenvalues, how to get eigenvalues, how to get eigenvectors. Okay. Let's have a break. Thank you. Here it's not F, it's component. Okay, this component actually is a linear combination of all y's. These are observed. Okay, it's just a combination of y. So this is not latent. It's not unobserved. It's observed. It's component of those observed variables. Okay, and of course we may have different components. Okay, from 1 to k. So we have k components. And then by combining different components, the biggest component, second biggest component, by combining all of these by using different lambda right here, we have the observed y. So that's a principal component analysis. Okay, principal component analysis, not factor analysis. So P again is a component, and R is a residual. This is a residual part. Okay, by combining these two, we have the observed y here. So it's very abstract. Let's look at the exercise. Suppose we have 3 individuals. We have x value, y value. We have 2 variables. We have 2 variables. Okay, x variable, y variable, and these are scores. The first individual of x1 is 1. Second individual for x is 0. Okay, third individual for x value is -1. And for y, we have this one. So if we combine these two variables together, then we have matrix A. Okay, A, we just put x variable here, y variable here. Then the question is that, okay, what are the cross product? Actually, this should be what is. I'm sorry, what is? We only have one. What is the cross product matrix of this A? Okay. Yes, I'm wrong. C. So we have matrix here. You want to calculate the cross product of C, okay? Or covariance matrix of this A. Okay. And then what are the eigenvalues of that covariance matrix C? What are the corresponding eigenvectors of that C? Okay, the focus is C vector. Okay, so matrix. Okay. So let's try to do some calculation here on board. And the document is also uploaded to ELC. Yeah, we can just follow the exercise. Well, we can do it together here. No. So that is our A matrix. Okay, we have 2 variables, x variable, y variable. So we have 1, 0, -1, -1, and 0. And we're trying to get the covariance matrix C. Okay, covariance matrix here. We have 2 variables. Okay, so after review the matrix algebra, okay, what is the covariance matrix of a vector? So it's expectation x minus the mu and the transpose. Okay, but the mu expectation actually is 0. Okay, for each x and y. X, the expectation mean part is 0, the y, the expectation is 0. So we don't need to care about the edge part. It's just the transpose of the transpose. Okay, so it's 2 by 2 because we only have 2 variables. Okay, the covariance matrix, or you can use sigma, but actually it's not the exact sigma. we can just use C, okay, just as the question talked about. So we can, we have the A matrix here, okay? So A transpose times A. Of course, we needed to use the sample size to rescale the sample size to get the covariance matrix. But in order to simplify the calculation, we just ignore the sample size. Okay, so we have A matrix is it's 1, 0, negative 1, negative 1, 1, 0 times, okay, 1, 0, negative 1, negative 1, 1. Now, what is that C? Okay, just do the calculation. It's already centered, just do the calculation. So we have 2 by 2, okay, 2 by 2. We only have 4 elements. So the first one here and here, okay, 1, 1, 0, 0, 1, 1. It's because negative 1, because it becomes 1, and 1 plus 1, it's 2 here. And the second one is this column, this row and this column, okay, negative 1, 0, and 0. So it's negative 1. This row and this column, okay, negative 1, 0, and 0 is negative 1. And this row, this column, okay, negative 1 is positive 1. And 1, 1, positive 1, 0, 0. That's it. This is a covariance matrix. Of course, we should rescale by the sample size plus U. But just keep this as our C. Then we can do the further calculations. It's much easier. What are the eigenvalues? How to calculate the eigenvalues of this matrix? This is our matrix. How to calculate the eigenvalues? Think about the eigenvalue definition. So we have, so here we have C, okay, C times U minus equals some eigenvalue. So we can use L or we can use lambda to show it. Suppose we use lambda. Usually we use lambda to show the eigenvalue. So we're gonna have lambda times C U here. So if you change the position, it's C minus lambda times identity matrix U is 0. So U is not 0, so you have to make sure this determinant is 0. So C minus identity matrix, lambda times identity matrix is 0 here, okay? Then you do the calculation. So we have C here. So we have lambda. So we have C minus lambda I. This is, okay, 2 minus lambda here. And the minus 1 here. Okay, minus 1 here. And the 2 minus lambda. Okay. So this determinant is 0. So if you do the calculation, okay, what is that? So this definition, okay, the determinant of 2 by 2 is 1 minus lambda squared minus the product of these two is 1. Okay. So you have what it is, okay? This is lambda squared minus 4 lambda plus 3, 0. Okay. This is the equation we needed to solve. What is the solution for this one? What is the solution for this lambda? Okay, it equals lambda minus 3 times lambda minus 1. So this is the same thing. So we have two solutions. Lambda equals 3 and the lambda equals 1. So if you want to get the solution of this equation, you see the same thing. So the biggest eigenvalue is 3. The second eigenvalue is 1 based on this equation, based on this matrix, okay, this C. So what are the eigenvalues of C? And that's it, 3 and 1. And next part, what are the corresponding eigenvectors? For each eigenvalue, we have eigenvectors. So let's just try to look at the eigenvectors. Okay. So again, based on the definition here, so we have C is here. times some vector u here. Suppose u is u1, u2. This is a vector, okay? So we have u1 here, u2 here, equals lambda. Suppose we are looking at the first lambda 1, the biggest one. So when lambda 1 is 3, then lambda 1 is 3. So it becomes 3 times u1 and u2. Okay, do the calculation. Okay, so what it is, this is 2u1 minus u2 equals 3u1. This is minus u2 plus 2u2 equals 3u2. Solve the equation, okay? u1 here, u1 here. So u2 minus, so it equals minus u2 is just u1. And here, u2 here, u2 here. So, u2 here, u2 here, yeah, here. It's the same thing. It's the same thing here. So we got this solution. So eigenvector, you can use a standardized version of the eigenvector because any u satisfying this relationship is the eigenvector. But if you standardize, then the u becomes, it's 1 negative 1 over square root of 2. Because you have to standardize to keep the length is 1. So this is the u corresponding to lambda equals 3. Okay. Then when lambda 2 is 1, what is the other u? This is a u associated with 3. What is the u associated with 1? The same thing. Just do the calculation. Okay. Now we have 1 here. So same thing. So we have, if it becomes 1, then it's 2u1 minus u2 is u1, and the negative 2u2 plus 2u2 is 1 u2. Again, solve this equation. Okay, so we have u1, u1 here. So u1, u1. So it's u1 equals u2. Here, u2, u2. So we have u2. I'm sorry, this should be u1. Okay, I'm sorry. Wait a minute. So this should be u1. Yeah, so negative 1 times u1. Okay, here, this should be u1. This should be u1. Because it's negative 1 times u1 plus 2u2. Okay, so here we have u1, u2. So it's the same thing. Okay, the solution is u1 is u2. So any kind of like a u satisfying this equation is our eigenvector associated with 1. But if we try to standardize it, the length is, we should still keep the length. Okay, it's 1, 1, negative 2. This is another eigenvector. Suppose it's g. Okay, so the standardized eigenvector associated with lambda 2 equals 1 is this vector. Okay, is this vector. And the eigenvector associated with lambda equals 3 is this eigenvector. So we got the corresponding eigenvectors. Okay, so for 3, it is this one. For 1, it is this one. Okay. Okay, now we are ready to get the components. So here we just got the eigenvalue and the eigenvectors. So what are the principal components? P1, what is P1? Use this part. P1 is just a linear combination of the observed variables. Okay. So how are we going to combine this xy to get P1, P2? So P1 is the biggest component, P1. Oh, thank you. Biggest component, P1 should correspond to lambda 1 equals 3. And the associated eigenvector is 1 minus 1. This is eigenvector. This is eigenvalue. So the P1 is combined xy by using the u here. So it should be the u1 times x plus u2 times y. u1 here, u2 here. Okay. So u1, we have the first component 1. Okay. X is 1, 0, negative 1 plus u2 is negative 1. Here we have negative 1. So y, we have negative 1 and 0. So it is this is the biggest component, okay? This is the biggest component. It actually is coming from, yeah, this is the biggest component. Actually, I have already, yeah. Actually, here, we can just see here it's clear. Biggest component coming from the linear combination of observed x and observed y. But what is the coefficient? Coefficient is just the biggest eigenvectors, okay, u1 and u2. So u1, u2, we obtained in the previous slide, okay. And the second component, so u1, u2 is here, okay, u1, u1, u2 here. So we have the x and y observed, and we finally get this form. Okay. This form. Over square root of the 2, negative 1, negative 1. P2 the same thing. For P2, it's another linear combination of x and y. P2 should be corresponding to lambda 2 equals 1. And the eigenvalue is v. It's 1. So these coefficients are coefficients for the second components. So it's v1 here, x plus v2 y. So v1 is this part x is 1, 0, negative 1. v2 is positive, okay, positive, and this is 2. Y is negative 1, 1, 0. So just do the calculation. So 0, 1, negative 1. So this is the second component. So this is the biggest component of P1. This is the second component. So what does that mean? So we have original x and y. Okay, these are original x and y. But actually, if you use this linear combination, we can get the biggest component of that linear combination. Okay, the x, y. The information actually is shared the most by this component. This is the second, this is also the smallest because we only have 2. The p equals 2. We only have 2 eigenvalues. Okay. Yeah, so this is the second p. This is second p, 0, 1, negative 1. So that's how we got the first component and the second component. This is just a very simple example. If you have large dimensions, so people doing the PCA, they just get the first component, second component by doing this way, okay? But this is not the end of story. So we're gonna use a PCA. We're gonna reverse back. The XY is a combination of P1 and P2. Okay? If you look at the equation here, So the original the x and y actually is a linear combination of the different components. So far, we just got the components. P1, P2, okay, P3, P4. We just got the component. So how about the reverse? Okay, got the original x and y by looking at these components. Then we're gonna use this is verified step. So what these are components? Okay, so this is original A here, and this is a vector. So we have the first eigenvector here, okay, U here. This is the second eigenvector, V here. So this is a U matrix, this is U matrix, this is the original matrix. So by doing the review, so we reviewed the eigen decomposition. So we have the A matrix times the eigenvalue. So we have the principal component matrix. So finally we have the X here, we have the U here. This is U1, this is V1, U vector, V vector. So we have this P vector. This is just a combination of P1 and P2. Of course, we have the square root 2 here. So combine the two components. Okay, so that's why we have P1 here, the first column, P1 here, second column, P2 here. Yeah, and we can verify. Okay, we can verify this component, first component and second component. So this is a P. So this is a P. Actually, this is a P. The transpose. Okay, the transpose of P times original P. So transpose of this matrix times original matrix, and here square root of 2, twice becomes 2, and then you do the calculation. So finally, we have the diagonal matrix of eigenvalues. Okay, so this is the diagonal elements. Eigenvalues. The first eigenvalue is 3. The second eigenvalue is D. It's diagonal. So we just verify these eigenvalue decomposition. Okay, eigen decomposition by looking at by using the eigenvectors. And then based on this step, we can reverse that. Okay, from P, how are we going to obtain the A matrix? Okay. Yeah, so by using the orthogonal view, so originally we have P equals AU. Okay, now we reverse that. So the inverse equals the transpose. So if we times the transpose at both sides, this becomes identity matrix because it's U, it's orthogonal. So A equals P times U transpose. Okay, so the original A is a P. This is the P we obtained. Transpose of U, okay, transpose of U. So transpose here, 1, -1, 1, 1 here. Is original A. This is original A. So by doing that, we got the original X here, original Y here. X here, Y here. Okay. So actually the X is a combination of P1 plus P2. This form, okay? Because we're gonna use this relationship. And why the second column here is just a combination of the P by using this second column. Okay, it's P2 minus P1. It's P2 minus P1 or minus P1 plus P2. This relation. So the original X and Y is a linear combination of different components. Biggest component and the second component. Biggest component and the second component. So this is a form of PCA of this form. Okay, so original X or Y. Of course, here we have Y, but in that case we have X, Y. All of these are observed values. Is a sum of different lambda. We use a U, okay? Components P1, P2, okay? So linear combination of these components, we have the X and Y. So this is example of the principal component. So the original X is the P1 plus P2 divided by square root of 2. Linear combination of the observed P1 and P2. There's no factor involved. In this case, no factor involved. Okay, all of these are observed variables, even P1, P2. P1, P2 are linear combinations of S1 and S2s. Yeah, so here. P1, P2 are linear combinations of S1 and S2. So these are observed, no latent factors involved. So that's why PCA calculates not factor analysis. Okay, so the factor loadings, we just do the eigen decomposition and get the eigenvalues. It's not factor loadings. Okay, it's not the parameters. Yeah. So finally, we have this coefficient. So let's have a review. So this is a true factor model. Okay. So the true factor model, the F here is unobserved. These are factor scores. Okay. These are factor scores, not just principal components. And also the lambda here is factor loadings, and also the E here. This is a unique factors. This is the common factors. This is the common factors. This is unique factors. Okay, not components. And if you have the comparison, this is a PCA. PCA, the P here is observed components. Okay, we just show the example. The P is a linear combination of the X and the Y, so it's observed. They are not factors. But for factor models, they are due to common factors and unique factors. So we have observed factor scores, unobserved unique factor scores. Yeah, they are different. Although the notation, when you look at the form, mathematical form, they are really the same, but the meaning for the calculation is different. Okay, I think I have already finished today's course. So any question for this? Yeah, if you want to do the exercise, you can just, I have already uploaded the document to the PDF. You can just, yeah, follow the exercise here. So starting from the original A matrix, you calculate the S matrix, C matrix, yeah, eigenvalues, eigenmanipulations. Yeah, how to solve that? Do eigenvalues. Yeah. Yeah, actually, this is a visualized eigenvalue and eigen decomposition. So we have biggest component lambda equals 3. And this is a second component. This is the biggest component. By doing the combination of x1 and x2, we have the biggest component. And the second component. So P1 and P2. Here, this is typo. Okay, I already corrected that. So in the original document, this is positive, so it should be negative, and here it should be square root. Okay, so this is a typo in the original document. Please correct it. Yeah. So I think we did the comparison between these two techniques. Okay, they are very similar. It's quite confusing, but it's different. Any question? We don't have any homework for today's class, but next week we will have homework 2. Yeah, homework 1 I will grade it back and send it back to you next week. Yeah. Any question? Okay, good. Then that's all. Yeah, that's all for today's class. Thank you. Thank you, all of you.
I saw it getting rough. And I knew you took it off your mouse and you don't like touching the mouse. I'm observant. I have kids.
Thank you.